Thank you. Thank you, Beeman. It's been 17 years since I met Beeman at my first meeting. I think it's 17. Maybe it's 16. So before I talk about modules, I'd like to talk a little bit about C++. You might have heard of it. I was at a meeting, a committee meeting, a couple of years ago, and we tend to have breakfast together. And that particular day, I had breakfast with Pete Becker. Pete Becker was the project editor for C++ 11, and I think he did a fantastic job. It's an unappreciated job. It's a lot of work, and there's times where you're the funnel through which everything has to go, and of course that's when you want to release a standard. So a lot of credit to Pete. But that time, Pete and I were talking, chit-chatting, and he mentions that he wrote an iPhone app. I'm like, oh, I wrote an iPhone app too. And so we start talking, and I tell him how much fun it was to write that app, and how unlike my regular programming job it was. And then he says, yes, he says, it's quite a change and a feeling of freedom and lack of stress when you don't have to worry about performance. I thought about that for a few seconds, and I thought, wow, he hit the nail on the head. That's exactly why I had so much fun writing my iPhone app. Because it was a very simple app where there's a bit of user interaction, and once I wrote it and the interaction was smooth, I was done. There was no expectation that, oh my gosh, I have to optimize this to get this 3 times faster. Because if I made it 3 times faster, nobody would be able to notice, because it's still interactive. Right? I'm not saying that every interactive app doesn't have to worry about performance, but this particular app didn't have to. So my day job is not like that. Although I'd like to make millions writing iPhone apps, I don't think I'm cut out for it. So my day job is to write compilers. And people are never satisfied with the speed of compilers. And I believe a lot of you are library writers. And to write a library, often you don't know who your client will be. Right? So you want it to be as high performance as possible. In fact, it was interesting to hear Howard yesterday talk about a self-move assignment and how he worried about performance so much that he worried even about checking for that case. He didn't want to spend that extra cycle because he knows his library is going to be used by thousands of programmers, and possibly someone will call that function a gazillion times, and a gazillion times a little bit of time is suddenly some noticeable time. So when you write your library, you want a nice programming language that's not going to penalize you up front. And so C++ comes right up as a candidate. It's actually surprising the number of languages that make performance a top priority. It's not that no other language cares about performance. I think most programming languages care about performance. But there's other principles that take priority. It might be purity, it might be safety, maybe some dynamic behavior or something. So for C++, performance is always an overriding concern. And therefore, it's an interesting language to write libraries. So, for sure, C++ has this wonderful language feature to describe libraries. No, sorry. No. We have a fantastic language to write libraries, but no way to describe libraries in the language. And so that's my segue to modules. Modules are really the language's view of what the library should be. All right. So what I'm going to do next is to show you a proposal that has evolved over the last couple of years, and at some point was actually scheduled for C++ 11. But then for scheduling reasons, for timing reasons, we couldn't spend more resources on it, and it was cut out at a meeting in Portland. And I'll introduce it to you by example. So in a few minutes here, you'll know everything there is to know about the modules as I envisioned them. So first, the way you write your module is we'll reuse an export keyword and say export name of my module : and those have to be the first tokens in your translation unit, and everything after that are contents of your module. There are two kinds of things in your two kinds of declarations in your modules. The public ones, which are the things that the services you want to offer to your clients as a library provider, and the private ones, which are implementation details. Of course, the private ones are still part of your module, and the client may actually have some inkling as to what's in there, but it's not going to interfere with your code. So what's the client code going to look like? Well, instead of having an include directive, you have an import directive. So import mylib semicolon. Import is not an existing keyword. For export, I managed to reuse an ill-fated feature. It bodes well for this proposal, I'm sure. So import is not. I'm going to find someone to donate a kidney. But it turns out actually import is an identifier that's used in some places. Particularly the Qt library has import members. So that is a concern, but I still think we should steal that identifier. And so that now I can start using whatever is publicly declared in the module. So for example, I have a type there called index type, and I make use of it here, and it just finds index type. And notice that my function is called select, and it conflicts with the signature of select in the module, but since it's private, there isn't a real conflict. It may have internal linkage. This module is actually not very well shared library, so it may have some sort of one of those funny shared library linkages, but there's not going to be a conflict. So how is it going to work? We're going to compile the module up there, and we want to keep all of our tool chain more or less compatible. So we don't want to, we want to change as little as possible. So it's still going to produce an object file or a shared object. So you still have that, but in addition, we'll generate what I call a module file, which is sort of a replacement for a header file. It describes the interfaces that are available. So the client, when you compile the bottom translation unit, you'll load that. But instead of being something that you have to parse and completely traverse before you actually understand the contents, this file is going to be structured so we can efficiently load it. In fact, it'll be structured in such a way that we can load only the parts that we need. So if you have, say, a standard library header with 10,000 interface elements, and you only use 10 of it, we shouldn't be spending all our time loading those 10,000 elements. We'll load the table of contents, and then we'll just get the parts we need. But there is a problem here. If you look at the declaration of index type, do you know what index type is? Size T. So I just try to avoid having to deal with modularizing the whole standard library up front, and so I made size T using decl type. Now, what is the type of size T?
It's implementation defined.
It's implementation defined. Now, if you have a compiler, you may well have a couple of different compilation modes. You may have a 30-bit mode and a 64-bit mode.
Yeah.
And depending on what you compile in, your size T might change. Which means that module file I talked to you about, if I try to do everything with a single module file, I'd be in trouble because I have to say, well, it could be either one of those types, and then you have all the declarations that depend on that, and you start getting a tree of declarations that's unmanageable. So in practice, what the module system will do, it will generate different module files for different compilation options as you go. It's just one of the technical difficulties when you try to develop this sort of system. And I'll come back to that, showing some various practical issues with that. All right. So now I want to talk about multi-level module composition. So suppose I have two modules, M1 and M2. Literally, in this case, all my examples are going to be very highly unrealistic, but I hope they convey the mechanisms that are involved. And so in this case, my modules M1 and M2 both export types. One is I1, which is int, and one is I2. I have a little bit higher level module called MM, and it imports both of these basic modules, M1 and M2. But one is imported publicly, and the other is imported privately. Those are different imports. Why are they different? Because when I import MM, any public import will be visible. Any public import performed by MM is also visible in the clients of MM. So I can use the type exported by I1, by M1. So I can use I1 here, and that's fine, but I can't use I2, that would be an error. I think that's relatively intuitive, but I was surprised to find that, for example, C++ CLI assemblies don't work that way. And it is an important transitive property of importing. All right, so we know about the general idea of public-private and how we import. Let me talk a little bit about the names of modules in this proposal. And you're having a great deal today because you're going to get 2 proposals for the price of 1. So I'm showing you the first one here, and then I'll show you another one a bit later. And then I'll shoot from the hip, and I'll make a third one. So here I have a module whose name is no longer just an identifier. It's 2 identifiers separated by a double colon. And in fact, my proposal is that you'll be allowed to use any number of identifiers separated by colons. And what's the meaning of this? Absolutely none. You give it whatever meaning you want it. There is no connection between, for example, a module called mylib and a module called mylib : basics. There's also no connection between a module called mylib and any other entity in your program called mylib. You can have a namespace mylib if you want to, and you can make it have a connection by virtue of declaring it only or defining it only in module mylib, but by default there's no connection. I won't always like that in the proposal. When we evolved this, at first we tried to tightly bind namespaces to modules. And it turns out people are using namespaces in too many different ways. Even the standard library doesn't fit very well in that model. So we're not making connection. In fact, namespaces are an exception to the general rule that every entity only has one module to live in. Right? There's a rule in the standard you probably have heard about. It's called the ODR, one definition rule. And the funny thing about it is it doesn't explain that everything has one definition. It explains when you can have more than one definition. But in the module world, we really want to have a true one definition rule, but we'll have one exception, which is modules. The reason why we'll have that exception is that suppose, well, I'll do it by example. Suppose you have the Boost library. And Boost is really a collection of lots of libraries. You wouldn't want a single module having all of Boost in it. Yet there's this namespace Boost that various libraries live in. You don't want to say, well, since Boost can only be defined in one place, you have to make a single module. So that's why namespaces are allowed to live across multiple modules. One way of thinking about it is that a namespace is more of a tag than a container. At least for compiler wise, that's a useful idea to implement this particular thing. All right, and so on the client code side, it's very much the same thing. You just use this name as it is. Notice that I qualify with namespaces. I don't qualify with the module name. The module name is never really used in your program. It's only used in export directives and in import directives. That's for the names of modules. But so far, all my modules have consisted of one translation unit. And that seems a bit too constraining. We're used to writing fairly large libraries. Maybe some of our libraries will be tens of thousands, even hundreds of thousands lines of code. We'd like to split them across multiple translation units. If you do that, then you have to give a name to each translation unit so that different translation units can connect. So the way I propose that is using this documentation to indicate submodules. And so now you can say export mylib.basics, which means this translation unit is part of a module, and we'll be able to refer to it using the basics name. And then I can put some stuff in there. I can have a private function helper and a public function index type, and maybe I have another part of my module where, say a select part where I'll implement a select function. And because I'm within the module, I have access to all the private members in other submodules. So I can actually use helper here, provided I have explicitly mentioned that I will import that other submodule. Any questions at this point?
This is by default private.
It is by default private, although I'm not attached to that particular
export in your bottom example should be a colon, right?
You're correct. Thank you. First bug reporting modules. Thank you.
I do not know.
All right.
Is Aspen.
By the way, there was a lot of discussion. We've been kicking this around in the community for a while, and there's been quite a bit of discussion about syntax issues. It goes forever. Whether you have a clone there, we put the whole module in braces. That stuff is definitely not solid. Okay, so we've talked about modules. There is an interaction between public and private in modules and public and private in classes. Now you know that in classes, access specifiers don't control visibility. They control accessibility. What that means is that everything you declare in a class in C++ 11, where it's private, protected, or public, is visible outside that class. And there's some pragmatic reasons why that is, but it's often surprising, especially to new programmers, because you really typically do not want private declarations to interfere with your code. Okay? So suppose I have this class here, struct S, one F taking a long and another taking a long. It's fairly easy to end up with an ambiguity trying to call F, even though the one that's private really shouldn't be considered once I'm outside the class. Now, public and private at the module level controls visibility. So if I had an F long and an F long at the module level, if you're in client code, you'll only see the public one. So if F long was private, it would not even be considered for overload listeners. Well, I'm extending that rule to private in a class context as soon as you get out of the module. So in other words, within this module, I can find the private F. In fact, I have to find it in order to be able to put this definition here. I couldn't find this S::F if it were invisible. So in order to parse this definition, I have to be able to see it. But once you're in client code for this module, private members become invisible. So when I call, on the S that's being exported from my lab, I call F42, there is no ambiguity. Even though if I had put that same call inside my module, it would be ambiguous because there's no preferred conversion between int to long and int to long. Okay, this actually is quite nice. It solves a lot of problems. I've had occasional bug reports that were hard to track down because of the accessibility rules, and this would probably have saved a lot of time. However, there are some idioms where it's exactly the accessibility and not the visibility property that's important. Now, a lot of those idioms are now taken care of in C++ 11 using the equal delete notation. So sometimes you make something private because you want to intercept attempts to call that particular signature and then say, no, you can't. Well, you can do that today in C++ 11, and it's better to do it that way, by making the member public and saying equal delete. So you'll have a clear indication that that's really what the implementer meant, that this should never call that particular signature. But there is another idiom, which is, I was actually not aware of it, but apparently it's pretty popular, which is to write a private virtual function and then have derived classes override it. And if you do overriding, you have to be able to find what you're overriding. The compiler has to know when I declare my D in another module. So another translation unit is using B as a base class, and I need to override F. Now, if F were invisible, as it would be according to the rules I previously explained, the compiler would say, well, okay, this is a new function. It would, imagine there is no override here. It said, there's a new function here. It's not virtual. It's got no connection at all with B. But in fact, I do want to find a particular virtual function F. Well, C++ 11 also introduced a new mechanism to indicate that you're explicitly overriding something in a base class. Now, I hate the syntax in C++ 11. Normally, it should come up here according to C++ 11. But I like it more there, so rebel that I am, I do it right there where I like it. And so when you have that indication that says, oh, I'm overriding something, then the compiler will actually look in that module file and find that private member. So that private member has to be there in the module file. It's just not shown in general. It's not visible in general. They'll find it and it will resolve the override tables, and it will work just as you'd expect. So I should mention there's a lot of little issues that came up as we worked out this version of the modules proposal. Often we were able to simplify or just say, you know what, this problem is too big, we're not even going to try to solve it. And so we're actually almost done with the whole proposal. So in this slide, I now have to deal with living in a world where most code is not modules. See, if we had had this on day one, you'd now be able to write modules and write nicely structured code, and we'd all be pretty happy. But there's a whole bunch of libraries out there that you'd like to use in your modules. And there's a problem. Suppose I say export mylib private, and I do pound include some header. And that header is not actually a module. What's going to happen? Well, all of those declarations in that header will be textually expanded in my translation unit, and will therefore be considered members of my module, which are clearly not. They're part of another library. So I need a mechanism to say, well, there are these things in a world outside that are not modules, but I want to use them anyway. So please be aware of them, part of the stuff. And so for that I have what I call the inline import, which is import open brace. And then you could put an include there, or you could write a single declaration, like I did printf here. And that is not a member of this module, but I can now call that API. Or there could be a type def in there that comes from somewhere else. So as you see it here, I do have a public member of my lab that calls printf, and that should work. This is an important transition tool for being able to, little by little, move from an application that has no module to one that transitions each library into a module. Now, there's another thing is there's a lot of code out there that does pound include. And suppose you have a nice library, you used to offer it as as C++ 11 library, so your customers are using pound include, and now you'd like to move to a modules implementation of your library. Well, all that code, you don't want to break it. You want it to continue to be able to say pound include. So what you do is you write your header file, instead of having lots of declarations in there, you just do import mylib, and whenever you do an include, you'll now have a very short header file, and you'll have an efficient import of a module. What's more, modules in this proposal are they're completely isolated from macros. In other words, when you do an import, and you had some macros just before that, those macros have no impact on the declarations of your import. Thank you. But conversely, if you do an import, there's no way for that import to bring in macros that don't mess up your code. It's both ways. No macros in, no macros out. But it might be that your library has some macros that you need to provide. Well, the module system for macros is called includes. So you put your macros in your header file, and you still have it. Now this seems like a good idea, but I'll come back. There's some practical issues and transition issues with this macro cleanliness. All right. So what have we bought? Okay. Well, let's talk again about those macros. And I have a message for you. There's one takeaway from this. Macros are evil incarnate. If we didn't have macro leakage across inclusion, we could actually provide a model system today completely transparent. So if as a compiler, I didn't have to worry about the macro changing the meaning of an include header, I would be able to pre-compile that header, and whenever you do include, I would efficiently load it up. So really, macros are the core difficulty in modularizing C++ and in efficient building. Last February, the committee had a meeting where we started talking about modules again. And Doug Greger, well, actually, I started giving a presentation, roughly what you just saw. And I mentioned an Intel project Intel, where in the, I think, mid-90s, they started tracking how much code was in the headers and how much code was in their implementation files. And when they started, it was 50-50. Now that's just amount of text. The header files get included over and over, whereas .cpp files, you compile them, once per build. So really, a lot more code was already being parsed as part of headers and as part of CPP files. Then 10 years later, they found out that it was about 90% of their code in headers and 10% in the CPP files. So then next, Doug Greger of Apple comes up and he presents some ideas about modules himself. And he says, oh, David says 90-10, but we at Apple, we're doing these measurements also. And typically, we're getting 99.9% code in headers and 0.1% code in .env files or .c files or .cpp files. So John Wigley, John, are you here? No. John Wigley, he's attending the meet, this week. He was sitting there, and he was sort of curious about that claim. So he writes up a little script, does a little measurement, and suddenly interrupts Doug as he's going along. He says, hey, I just checked. You're right. I just checked my own project. It's 99.997%. So really, we have a lot of code in our header files, and we can't pre-compile it. And that's slowing down our builds to the point where a lot of projects, that's their main concern. They don't care about optimization. They don't care about fancy techniques. Every day is a struggle to being able to build their project overnight. But also, it really affects the programming tools that we can have in C++. It's sort of funny that we have a language here that's been around for 30 years, and there's some really interesting tools out there. There's some much younger projects, much younger languages that have tools that are very impressive compared to what we can do in C++. And most of it is because we have difficulties anticipating what macros will do to source code compile we'll eventually see. So the big deal about modules is that you could have fast builds if we had it. How's that?
If macros are so evil, will we have a replacement for a facility like a cert that really does depend upon macros to have its semantic?
So the question is, would we have a cert, a replacement for a cert? And the answer is, I think not. It is okay to have a few header files out there. I don't think we'll be able to kill macros. So a cert will remain a non-modular header. It's my guess. But perhaps I'm wrong. In fact, I'm going to come back to that because I'm going to show you a second proposal for modules. And although it introduces a level of macro sanity, it's a little different. And it might be enough for a cert. Now there's more to modules. This is, fast build is sort of the signature thing, the thing you'll most directly notice if you have a good module system in C++. But by having imports, we now have a clear model of what is our kernel code and what is our library code. Which means we have explicit dependencies between translation units, between libraries. And that's really interesting because once you have that, you can make a big step forward with respect to the ordering of initializations. You might have run into problems where you have one library that has some dynamic initialization that needs to happen, and another one that relies on it and needs its initialization to happen after the first library. But because there's no way in C++ to actually say that, you end up with problems sometimes where you call into a library that hasn't been initialized yet, and crashes ensue. Well, I think with modules, because we have these explicit dependencies, we could solve that. And it's not trivial. There's some rules that have to be put in terms of avoiding cycles and things like that. I've learned a lot from a man called Jean-Marc Bourget, who is a French representative in committee, and has helped me a lot to understand all the trickiness here. But the good news is there is hope to at least make it much better, if not airtight. And then this, I think, is actually something that's close to the heart of Dave Abrahams. There's a lot of properties of simple functions that the compiler can deduce. For example, there's a lot of functions that, without you saying anything, the compiler actually knows it won't throw an exception. The compiler might know it doesn't access globally available memory. It might only read some memory or not even touch any memory. You might find a lot about the way it uses pointers, and notice that there's nothing funny going on. Now, it'd be nice if you could pass that on to client code so that the client code compiler can say, oh, I can optimize this much better than with no assumptions at all, because I know you're not going to mess with my variables, for example. And so I can reschedule code across the call. Now that's the kind of optimization a compiler can easily do if it knows the properties of the function. Now most commercial compilers today have what's called whole program optimization or link time optimization. But in practice, it's not used that often because I think it scales relatively poorly. And now different, I know some compilers claim that they're doing much better at that, but still in practice, people don't like to turn on link time optimization. In part also because it really increases your build times. But in a module system, these properties can be communicated through that module file I talked about earlier. And so you'd have increased runtime performance with pretty much no build time increase, or in fact, improved build times. All right. So, how do you like the module so far? Any questions?
You mentioned that people did a study and most of their code was in headers, and I suspect part of that was because most of their code was templates. So you have not shown exporting templates from a module. How does that work?
It just works. Imagine having included it. It'd be the same thing, but no macros have any effect on that template. Now there are some subtleties. There are funny things like friends. And what does it mean to make a friend t, where t is a template parameter? And then suddenly you're outside the module, but I never made the privates available because you can't make it a friend. So there are limitations in very corner cases, in very odd code, and we can actually solve a lot of those limitations. But mostly it just worked the way you'd expect.
There was a Google Summer Code project a couple of years ago trying to emulate the module system of you had back then using essentially generating true files and the source files from it. Is the project still going on, or is it just dead?
Well, I saw the project going by. I think someone might have sent me an email about it, but I was not actually involved. I may have sent them a document that's about it, so I don't know. I don't know what the situation with that is.
Yeah. I mean, I was loosely connected to that because the guy was using Wave at that point as a preprocessor and to cause that. Would that be a viable option, just to go back to that and just build an experimentation ground, or even be able to get backwards compatibility to all the compilers to generate the old include files from an existing module so you can support compilers not supporting modules to the library? What's your sort of that?
Yeah, so the question is, could we sort of simulate or emulate the idea of modules using header files and maybe small preprocessor extensions? And the answer is, I think to a large extent, yes. And certainly it could be if you want to implement implementation experience, or rather usage experience, but we don't want to put the full cost of implementing it, that might be a step forward. However, I'm going to talk about something else later that might sort of make the whole point more. I know there was a hand on the right earlier. Go ahead.
Here's what the use case was for private exports, as opposed to just putting private things in a non-exported header file. Like there's a private section of the export, but the importer can't see it. That seems.
Oh, well, the reason is I want all my code in one place. Okay. I don't want to be forced to go move all my private stuff in some other file.
Yeah, I guess it's hard.
Now, you notice also, like, I had this issue with private virtual functions, and I have to actually export those.
Yeah.
There's a couple of other cases. Like I mentioned friends earlier. You might make like suppose you have a public inline function that calls a private function. That private function has to be in the module file. A whole bunch of little things that they're not visible to your code per se, but the compiler has to know about it. I don't think know the order, so I'll go from back to front.
Instead of imports, you use include as a keyword, which might be a lot of the time people probably don't use it.
We might. I haven't thought about it.
Strikes me as really wonderful work. It also strikes me that it's complex enough that there's no way to know, to spot a lot of problems until it's implemented and used. So have you given any thought to a process of essentially verifying it by use before it becomes standard?
Yes, I should start implementing it, but I'm going to show you later. Doug Greger is racing far ahead of me. So you'll see we're in a much better position than it might look like so far.
So if you consider templates in modules, how are they not vulnerable to problems of old exports? Are we never going to see those problems again?
What were the problems of old exports?
There was paper about it.
Well,
Because I never already compiled it.
Right.
Export.
So
Basically, there were products to vastly increase build speeds, and in practice, they didn't really do any.
they were expected. They were actually not promised. They were expected to increase build speed. They didn't. That's because it's not. See, export was an attempt to modularize just templates, but not functions, not ordinary static data memories, things like that. And so it didn't work very well. This model, think of it as include, but cached. Right? So some people think of it as precompiled headers. Now the problem with precompiled headers is that you have to, you're precompiling a whole prefix of a translation unit, and you change one header, and basically everything goes, gets rebuilt. It's kind of painful. Here, you change one header, and only that one header has to be recached. There's a hand in front. Yeah.
Is the module file that you speak of exactly the publicly well-defined interface that people can utilize to build tools and other things?
Thank you so much for leading me to my next slide. Okay, so now we're going to talk a little bit about the module file. I stole a slide from a presentation I gave about the horrors of compiling C++. This is a sketch of your textbook compiler. C++ compilation is not your textbook compiler, but this will actually do for our discussion. So compilers typically are broken down in two parts: the front end, which deals with the language itself, and the back end, which deals with the target. Ideally, you would want the front end to not know anything about the target, and the back end to not know anything about the language. In reality, it's not like that. For example, the front end has to know size of int. So in C, C++, it's not like that. Some languages do really achieve a very clean separation there. And so then you have a pipeline, at least in principle, a pipeline of operations that happen to compile your code. Let me go quickly through it. You start with your code, which is treated as a character stream. You think that's simple, but it's actually incredibly complicated because some people write different header files in one encoding, and then they include in a file in another encoding, and so on, and they don't, it's pretty complicated. But let's forget about that. You transform those characters into tokens. The tokens get, you find the grammar in them, so you create a parse tree. Then you figure out semantics, so you annotate the parse tree with the meaning of all these, the nodes in your tree. You might do some diagnostics, possibly do some things on the side. And then you have the annotated parse tree, and you'll pass that to the backend. Typically, you don't pass the tree itself to the backend. Typically, you'll have some intermediate representation, IR. And that goes to the backend, which first will look at all this IR, will rearrange it, optimize it to some degree. So you have optimized IR. Then it maps that to your target architecture. That itself is actually an important part of optimization, so the scheduling, register allocation, a couple of other things that happen at that point. And finally, you produce some object code. All right, today's model of libraries, which the language is unaware of. The language has no idea what a header file is other than a bunch of text. Has two parts. One part is the object files. At the very bottom, they're completely processed, almost. The linker still has to do some work, and unfortunately, that's getting increasingly costly. But at least you don't have to go, once you link, you don't have to redo all this work through the pipeline. Header files at the complete opposite end. We have to redo all our work. Now, when we import modules, we'd like not to have to redo all this work. We don't want to tokenize, parse, do semantic analysis, and so on. Right? We really want our modules to be here, at the level where the front end still understands it, because if you give it IR, the front end doesn't, IR is sort of a lower level representation. You cannot necessarily extract everything out of it. So you really want that annotated parse to anyway. So we'd like our own files to be there. Now that's a problem, and Jeff just alluded to it. Because the format that a compiler uses internally is proprietary, it's compiler dependent, it's actually version dependent. I make, on a work day, more likely than not, I will change the internal representation of our semantic trees. Right? And it's not human readable. We have a tool to sort of turn binary stuff back into some kind of readable format, but it's not very pleasant. Right? So although we really want our module files to be that kind of representation, it's very unfriendly. If you're a lint vendor, like you want to sell a static analyzer, today you just work with source. But if you start distributing files and modules with binary files, they'll have to reverse engineer everything. It'll be a nightmare. Instead of modules improving the tool landscape, they'll actually worsen it. So therefore, our module files will have to be character strings. In fact, they will look a lot like header files, but it will be generated by the compiler. But it will be readable and it will be generated from your source. And what's going to happen, and it's going to be mostly C++ code, so it will be compiler independent, version independent, and it will be human readable. It will be standard. But the first time you do an import across all your projects for a particular set of command line options, the compiler will have to parse it and do this whole first part of the pipeline that I was showing earlier. But then it will put it in a cache on the side. And next time you do an import, either for that build or for another build, the independent build, you'll have a precompiled module and the import will be near instantaneous. All right. But so far, I've shown you modules as I imagined them. So let me talk to you a little bit about the history of this proposal. When I started learning C++, about 20 years ago, the thing that caught my eye were operators. And I thought, oh, I know, I'm going to write a matrix library. It's going to be fun. It's going to have operators, multiplication. I'll even, have a division to solve equations and whatnot. I was very young and naive back then. And within a day or two, I realized, oh my gosh, I'm generating temporaries all over the place. This is highly inefficient. So then I started working on that. And eventually I came to a place where I decided I would propose metaprogramming facilities as a first-class facility in the language. And so there is actually somewhere on the web an old proposal of mine called Metacode. It wasn't really formally proposed. But the idea was that you'd be able to write. My purpose really for it was I'd be able to write my matrix library, which that's pretty much all I've been working on for the last couple of decades. By building in an optimizer in my library. So you'd write an expression, a matrix expression. I'd map all of that on Metacode, and then my Metacode would figure out the best way to reorder the operations and allocate the various temporary matrices so it's really minimal. And then I realized I actually implemented about half of that feature, enough to be able to start testing Metacode functions. And I started realizing I'm putting all this code in my header files. It's already bad, but with Metacode, it's going to be an order of magnitude worse. Because pretty much all of your Metacode is going to end up in header files. Compilation times will be horrible. I need to come up with a better idea. And so I started with a scheme that implemented modules on top of namespaces. And it wasn't very good. But shortly thereafter, we had a meeting in Kona. And I was sitting next to Dave Abrahams, and we were looking at some hairy problem. And Dave says, gosh, this language really needs a module system. And Björn Strostrup, the inventor of C++, who's chairing the meeting, says, well, he says, I don't disagree, but we have nothing to start with. We have no, we don't really know what we even mean by that term. And so I was sitting next to Dave and said, I said, actually, I have this little sketch here for modules for medical. And I show it to him, and over the break, he goes to Björn and says, David has this thing. You should take a look at it. So Björn says, well, we have a little extra time. David, why don't you come up and present it? And I presented it, and it was strong interest in it. And so I was encouraged to evolve it, and with the help of a lot of people like Peter Dimov and David Abrahams and a lot of other people, evolving what you're seeing so far. Then it was actually at that point slated for C++ OS. But then we ran out of time, we cut out a whole bunch of features. Concept stayed that one meeting, but modules were gone. And it went to sleep. And then last February, the committee decided, well, let's take a look again. And we're looking at producing 2 standards, one in 2017, one in 2022. Those are tentative dates. 2017, we're looking for relatively small core extensions, and then anything that's bigger would have to go in 2022. So again, we had a little extra time. We looked at, I presented a bit of modules. Then Doug Greger got up and said, well, we at Apple, we're really having this problem with header files also. And I mentioned earlier this 99.99 whatever percent of code in their header files. And actually, they have this without templates. They have this with just the Objective-C frameworks. So he says, so we have started working on this for real. And so he says, we have an idea that we're implementing Clang, and I'll call that proposal Clang modules. Now, Clang modules approach the problem differently. For Apple, it's really important that they can use this from day one. And not just for Apple, for a lot of people. It'd be nice if all this code that you've written could be seen as a module if you've been reasonable with your header files. And most people don't do really weird things in their header files. So he has taken the approach that you designate a group of headers for your library as a module. So imagine you have a directory, has a bunch of headers, and 4 of these headers will be one module. Well, in that directory will live a file, and it's called module.map in the Clang implementation. And that file describes how to group different headers into a module. I'll show you an example of a module map file a little bit later. And it follows the same principle that I talked about earlier, the idea of caching precompiled modules. In fact, it even automatically keys off pound include. It has an explicit import syntax, a bit like the one I showed earlier, but it also works with pound include. So if you turn on modules and you do pound include, normally the compiler just goes down your search path, finds your header file, and brings it in. But if you have a module map file, the compiler notices that your .h file, that a particular file that you're including, is one of those files that forms a module. And instead of just actually including a file, it will compile all 4 files as one module interface set, so a module file, and put that in a cache. And it will just load that whole assembly of files using a module just like in the other proposal. All right. Any questions at this point? Just making sure you're seeing how this works.
When you mean cache, is it going to live on a file?
Yeah, it's a file system. Think of it as a precompiled header, except you don't have the constraints of a precompiled header. And it's done automatically. Now, there's a couple of interesting things about the Clang approach. One is, if you have macros in your headers, you have to make it up, because they really want us to work transparently. So code that already exists today has to work with this. And of course, code that exists today does have macros that Clang code uses. In fact, if you think about C headers, a lot of the standard library functions in C's, standard permits them to be macros. So they have to make it out of the module. And so in the Clang module system, macros can come out of modules. Now, macros that you define in your code will not affect the import. So you didn't have that cleanliness. But macros that you define on your command line do make it. And in fact, for every different set of macros that you define in your command line, it creates a separate module file. So to come back to Elsder's earlier, if you think about assert.h with ndebug, and you only control it on the command line, this scheme actually solves it. Let's look at what a module map file looks like right now. So here's my attempt at making a module file for the standard library. Now I should say there is an implementation of this today, and it works quite well for C and Objective-C. And I'd encourage you, if you're familiar with building Clang, to build the current the Git version. I don't know if it's in any release, if the modules are in any of the releases, maybe the latest, I'm not sure. They'll be in 3.1, okay. So to give it a shot and try it out, it's kind of fun to see that work. This will not work, but I'm just trying to illustrate with a C++ example rather than an Objective-C example. So this map says, well, there's a module SCD, and it contains submodules. And for example, it contains a submodule stdio, and that's a module you format by pre-compiling header stdio.h. Now there could be multiple headers in a single submodule, or it could be multiple headers in the top level module. But in this case, it's just one header. So you can import std by itself. If you do that, all of the submodules will be imported also. But you can also import std.stdio, and then you only get the stdio part. Notice that this is different from the proposal earlier, where the colon had no effect. Importing, say, mylab did not imply that you imported also mylab colon anything. It's a little bit different. Now you can put, in addition, you can put requirements in modules. So for example, you can say, well, std also has a module vector, which whose contents is basically the contents of the header vector. But you shouldn't try to import this if you're not compiling C++. So there's a requirement for C++. And the client compiler has a bunch of those requirements, things like Objective-C, Objective-C++, and so on. There's also the idea of an explicit module. Say, for example, IOStream, you don't want to automatically bring in all the consequences of including or importing IOStream, because remember here, it is very much like including. So you say explicit, and that means that even though it's part of the module std, when you do an import of std, you don't get IOStream. You have to explicitly say import std.iostream if you want that part of it. We also have the idea of transitive imports. So if you want an import of IOStream to also automatically import locales, for example, you have a way to express that in the module map file. Now the module map file lives completely outside the header itself, which means that you can introduce modules in a library that doesn't belong to you. So it's very powerful in terms of moving forward with modules and migrating towards a model with modules. In fact, the Apple system is even able to fake up a module map if it recognizes certain structures on your system. For example, if you're familiar with macOS, it has this notion of frameworks, which are directories that are mostly containing libraries and header files. And if it recognizes that you're trying to use one of those in include, and it doesn't have a module map, it will actually make a module map for you on the fly. Not necessarily on the file system. I don't think it gets told in the file system. But to compile these as a module. And so it starts treating those things as modules. And Doug mentioned that it's actually working really well. It's already competitive on real projects. These are not C++ projects, but on real projects, it's competitive with precompiled headers. And that's without having done any tuning, whereas the projects were tuned for precompiled headers very, very carefully. So let's talk a little bit about the strengths and weaknesses of this alternative approach. And one is availability. This is already available today in C and Objective-C, and I've got good hope that it's going to move quite quickly forward from C++. That's really important for us to understand what exactly it is that we want out of the module. It's nice to theoretically think about these things, but it's even better to have some experimentation today. Now, the ease of transition is fantastic with this system because, like I said, you can transition to modules any library that's out there that's been reasonably written, you know, unless you do very odd tricks in your header files, you're going to be able to transition to this module system without too much pain. In fact, Doug has gone out of his way to find ways to even accommodate certain weird things that happen mostly in system headers. It's amazing how, you know, some of the things that people do with macros just to define size t. Now, in terms of ease of programming, I think that's debatable. I like my code to all be in one place. I like, in terms of the model, I prefer the other model. But it's still quite usable. Now, there is no visibility control at this point in the system. However, there's work going on to do some of that. In fact, I think I might be wrong about that. I think Channel Cruz has told me that. Channel, are you here? Oh, yes. I think there's some already for macros, so you can already control macros as an extension. So your module map may not control visibility, but if you're willing to use some extensions in your source file, you can say that a certain macro is private, so it doesn't come out of your module. But by default, they do leak out. Now you can easily imagine that you could add some facilities to a module map to basically say don't export macros by default, or only export the following macros, which I really intend to make available to my client code. Now, perhaps the most fundamental difference between this approach and the other approach is that in this approach, modules are purely an interface mechanism. The module system never sees the implementation. So you can't solve the initialization argument, because the initialization argument is really about dependencies between the implementation, not dependencies between header files. So that is something that would be more challenging to retrofit to the client module model. And similarly with the idea of cross-translationing properties and optimization, that is not something that easily comes out of that. So then, could we do something about bringing those two together? So when after Doug showed some of this in Kona in February, we went to a chat, and Chandler was at that meeting. Dave was there, and we talked about, well, could we possibly bring those two together? And Chandler in particular had a couple of great ideas, and now I'm shooting from the hip, and I'm showing you what perhaps we could do. Okay, so I just made this up yesterday. But imagine that we have our module map, but instead of having a file that's sort of this separate language on the side, then we could say that the first model I showed you, the one with export keyword and so on, that we could annotate it to say, well, you're not going to get from me the implementation. I'm only going to give you the interfaces. We could also annotate it to say, well, I have to export macros here. Could we rewrite this in a way that kind of looks like that model? Could we make it look like this? So I still have my export std colon like I did before, but now I have an attribute on there that says you have to map includes as if they were directly imports. Right? And then I could nest exports to make submodules on the fly. Remember, in my original proposal, submodules were translation units. But maybe I could say, well, you can also do parse translation units. So I'd be able to say export.stdio. And I could say on that export, well, for this particular one, I want to export macros. And I could have an vector, much like I had in the module map. I could put some annotation, and maybe I don't need the macros from vector. So that one I just export, but I say that it has to be C++. And so you can see how we could make it look like the other module. In fact, for the compiler, it would be very much the same thing. It would just not have the implementations. And so it couldn't do things that it would do with the implementations. But it could still make them members of the modules, pre-compile them, create a module file, and it would be golden. That's sort of a vision for what might be the future. So, want some more?
Yeah.
Well, unfortunately, I'm out of slides. But there is a study group in the committee called SG2. Doug Greger is appropriately the head of that group. And so if you're interested in that, I recommend you try to get into the reflector for that and see what we'll come up with. Hopefully, I'm really hoping for something by the C++ 17 timeframe because I want modules now. Thank you. I saw a hand in the back there.
In that last slide you showed, I'm wondering how you deal with transitive dependencies.
Sorry, say that again?
In that last slide you showed, I'm wondering how you deal with transitive dependencies. So if you export, you had the example of exporting stdio with macros enabled. What if there's a transitive dependency in another file that has macros disabled, for example? Is it all packaged up?
Right, so that's a good question. So as I said, I came up with this yesterday, just made on the fly, based on some ideas from the channel. I'm sure we can come up with notation to indicate those things, just as it was in the module map file. So I didn't actually explicitly translate that, but I think we can solve that problem. And so that's the kind of questions we're going to have to ask in SE2 and see if we can come up with solutions backed by implementation.
You talked about cross-translation unit optimizations.
Right.
That could be a major headache for ABI compatibility.
Yes.
You make some internal implementation change to some module, and that propagates to all your clients.
That's right. But because you now have explicit dependency, your build system is aware of changes. So if you change something in your module, your build system is going to rebuild everything that depends on it. But you may not want it.
You may not want it.
So presumably your compiler will provide you options to say, I don't want this.
Right.
Yeah, you're right. It's a double-edged sword. Back?
In the first part of Mario's proposal, how does it deal with conflict of name, one vendor has a module with this name, I have this one, and all the search back.
So modules are looked up pretty much using search paths, not like includes. Conflicts are like namespaces. There's no, it's basically choose your names carefully. Right? If you're Microsoft, it's probably not nice to call your modules, so that, does that answer the question?
Sort of, except it's not a string, so how would you figure it out? How would you, let's say that in my search pattern, there are two different.
Oh, so assuming like you have search paths and you have two different modules called X.
Yes, how do I get the other X?
It's a good question. Right now, you get the first one. So there's nothing like include next, for example, as is the case in some C++ compilers. So the problem is equivalent to the one in include headers today. But you can imagine putting more control about the place where you import it in the language itself. Well, that might not be, it might be kind of messy. You might prefer sort of out of band indications for where you find your modules.
I don't think there's a point to solve this problem. I mean, look at every other existing programming language. They all have this problem. And none of them solves it. So apparently it isn't actually that big a practice problem. I mean, Java doesn't solve it. It solves it by convention.
Right.
By putting some unique part in it. C#.NET doesn't solve it. Python doesn't solve it.
Microsoft does the reverse DNS thing.
Java does that, but it's a convention.
Yes, absolutely.
So, and Python doesn't, Haskell doesn't. So I don't think it's really a problem in practice. It's just a matter of convention that you don't use conflicting modules.
Thank you. I had a hand over there, and then.
I think one way to deal with that would be to allow something, some sort of extension to this that allows you to rename a module as you import that.
Aliasing.
Yeah, aliasing.
A bit like feature. Also, there's plenty of ideas. Now, I do think that in order to move forward with any proposal, you have to make it as small as possible. It's very tempting. Modules created this new world, and so it's very tempting to say, oh, in this new world, can we please put minor amendments that's going to make this solve this other problem. And I think we want to stay clear for that until we actually have modules in the language. Then we can start binding up whatever we want. Then,
So I think you just answered my question, but I was going to ask if we thought about addressing the versioning issues with modules.
yes, I have thought about it. It scares me, so I'm going to stay away from it. Yes, it's a very tricky problem, and I'm not sure we can even solve it using modules. I'm hoping there is no solution that would require us to know the solution ahead of time to design modules. So I'm hoping that we can make one step having modules somewhere around this level. And if there is a solution for versioning, then we can still migrate forward and not find out that we painted ourselves in the corner. So definitely tricky and unfortunately really important problem.
So will the compiler track timestamps of files in order to know when to rebuild
I think that would still be left to your build system. So not necessarily the compiler itself, but whatever system is aware of a module. Actually, no, the compiler will, for the module files, it will track timestamps. And so I think the client implementation does stats and caches stats.
So what the client does is it stores a lot of information in the precompiled module, like timestamp of the origin source and set of macros and the compiler options. And basically, when it tries to read it, it checks, and if it's out of date, it rebuilds.
Right. But on top of that, I think the build system will also, just like it now checks for dependencies on header files, it will check dependencies on module as well. I was there, I think.
Once modules are a solved problem, are we going to hear more about metacode again?
Yes.
Excellent.
I had two comments. One, just a response about the timestamps issue. Just to be aware, we do know that timestamps aren't necessarily sufficient. I talked to Doug about this when he put timestamps in, and he was like, I want a prototype now, and so I think there is some idea to do more careful checking with digests and other more rigorous checking long term. But timestamps work and they're fast. So the other thing I did want to say is when Vijay and I were talking about this particular kind of hybrid proposal, something that you didn't talk to, but I think is the most exciting aspect of it is that if I'm writing a library and I port the existing library to this system, I can start adding new code or replacing small pieces of the library with the exact syntax you proposed at first. And I can start incrementally getting all of the additional benefits.
Right, that's a good point. I didn't mention that. But since now we're in that export model, you can imagine that you can mix it up so some parts will be using the include mapping, and some parts you just use all that syntax that I introduced in the first part. And you could do this gradually. So the new code could use that, and maybe, as China says, you could move stuff out of headers and into here little by little. I think that's all I have. I'm not sure. Well, thank you.